Okay, so I think we can start. So once again, good morning or good evening to everyone. And my name is Petracca, and welcome to this new webinar. I'm going to share my screen. Here we are. Okay. So today's webinar is about nonlinear time history analysis. And basically, I will give you a brief introduction because I think that most of our webinars, most of our previous webinars, were only about static analysis, static or quasi-static analysis. Probably only one of them was on dynamic analysis. So here I will give you a brief introduction about dynamic analysis, what's the difference between implicit dynamics and explicit dynamics, how you can do them in OpenSees. And then we will start with implicit dynamics. We will perform a nonlinear time history analysis of our bridge with RMB devices. Then we will start including complexities one at a time. So at a certain point, I will show you how to include contact between bridge segments, for example, to simulate the pounding between the bridge decks. And then I will show you how to run multiple analysis with different accelerometers, because most of the times when you do a nonlinear time history analysis, you do not apply only a pair or a triplet of acceleration. You need to use more than 3 or 7 or even more. And here I will show you how to start a model in OpenSees, the sequential OpenSees, so not in parallel. And then I will show you how to use OpenSees MP, so one of the 2 parallel versions of OpenSees, to use the same model and run a parametric analysis where the parameter is the accelerogram. Okay. Then at the end of the webinar, I will move to explicit dynamics. Now keep in mind that this one will not be a webinar on explicit dynamics, because explicit dynamics, it's a complex world. It will take a lot of time to explain how explicit dynamics work. So it will be just a brief overview. And I will give you a simple example of a fast dynamics. It will be a blast simulation on a masonry wall, sequential one, and then a parallel one. And I will take this example to show you also how you can customize the STKO workflow to include your own scripts. For example, here with my own script, I will perform element removal based on a custom user-defined criteria. Okay. So let me start with the brief presentation. So as you know, in most of our previous webinars, I have to start this video smart. Okay, they should start. I don't know why they are not starting now, but anyway, let me see. They can start from here. Well, probably there is some problem with the video codec when I am on the remote desktop. But basically, these are some examples of our previous webinar. Probably this one was the only one in dynamic analysis. It was an example of solid structure interaction. And this one instead was a dynamic analysis of a micro model of a masonry wall. And then mainly we have been doing static analysis, also detailed analysis, but these were static. Okay. So you probably all of you know the differences between, at least from a practical point of view, between a static and dynamic analysis. So let's give a brief overview of what is an implicit dynamic analysis. So as you know, the equation for a dynamic problem, if for simplicity we ignore damping, contains several terms. So the stiffness matrix and the displacements here in the elastic form, or in the general nonlinear fashion to be the internal forces. But it also has other components depending on the inertia effects, for example, the mass matrix and the acceleration. Then the complete one will also include damping and velocity. But now for simplicity, we do not include them here. And as you know, when inertial effects are low, so basically when you are running slow problems, quasi-static problems, the accelerations go to zero, so we have the standard static equation. So the internal forces should be equal to the external forces. Now, this equation should be integrated in time, and we can distinguish between two different kind of time integration scheme, and OpenSees has both of them. The default one that we use 99% of the cases, they are called implicit time integration. One example is the average acceleration method, which is basically the Newmark method when you use the beta and gamma parameters equal to 0.5 and 0.25. But there are other, many other time integration schemes. Now, the problem with implicit solution is that the internal forces and the displacement that you have to solve for at time n+1, so the solution for the next step, will depend on some quantities from the previous step, okay, and the external forces from the current step, okay. Now, these one are known because it is the right-hand side of our equation, okay, but the internal forces, if this problem is nonlinear, the internal forces depend on the displacement that we have to compute. So basically, we need to perform nonlinear iterations, okay? And then we need to find equilibrium. Now, this is fine, but and we do it all the time. Basically, when you have, when you use the Newton-Raphson method to iterate or any other kind of Newton-like methods, they do not guarantee that you can find a solution, because to find a solution, the problem should be is nonlinear, but should be smooth enough, because basically the Newton-like method, they require the derivative to be computed, and this derivative should be sufficiently smooth. Otherwise, it will be difficult. It will struggle to find a good solution. Okay, and then there will be the explicit time integration scheme, which is completely different, and I will talk about them later on. Now, the disadvantage of implicit time integration is that you have to iterate. Convergence is not guaranteed, but the nice thing is that they are unconditionally stable. It means that the stability does not depend on the size of the time step. So you can choose whatever time step you want. And of course, you have to seek for convergence. But if the time step is not extremely large, in the sense that Newton-Raphson is able to find a converged solution, you don't have to worry about the size of the time step. This is not the case instead with explicit dynamics, okay? So without wasting too much time on mathematics here, I will soon go to the first example, and I will show you how to perform a nonlinear tenor analysis of a bridge with other V devices, but this is not so important. We are not going to talk about isolation systems. In the next webinar, instead, we will do it. Okay, so I will show you a little bit the structure of this folder that you will find on our website. For the attendees that are new to our webinars, you can find all the webinars, all the previous webinars on our web page. So askthesoft.net. You can go under products, training, and under training you have e-learning courses, okay? Now here you have the current one and the following one, and then all the previous ones are here. You have a button to download the contents and files, which are basically all the input file that I'm going to use in this webinar, and also the presentation and any other support file. So it will be available tomorrow here. And then there will be a link on our YouTube channel, okay? So if you miss this webinar, don't worry, tomorrow you will be able to see it. Okay, so I will just show you a little bit the structure of the content files. We will start with an implicit example, so this bridge here. So the first folder here is the implicit bridge, is the first example that I'm going to do. Then I will add contact, and it will be in this folder, implicit bridge CT. Then I will show you how to run multiple analyses using the same model, and this will be an implicit bridge multi. Okay, and then finally we'll show you an example from explicit dynamics. Okay. Okay, so let's start with the implicit bridge here. Now I don't want to touch this folder, so I'm going to copy the input file in an auxiliary folder, which is aux implicit bridge. Okay, and I'm going to copy the input file here, so we'll start from this input file. Okay, let's open STKO. Okay, here we are, and we open the input file. So as I said, I'm going to open the one that was here, but in this auxiliary folder. So we open up implicit bridge. I'm going to the properties so that you can see what's going on here. Let me switch off the grid. We don't need it. So the model is already built, so we'll not waste time doing the modeling. Instead, I will explain you how I model these things, okay? And then we will set up everything for the analysis. So the entire model is made with frame elements, okay? So if we go in the geometry tab, you can see the geometry itself. Now it is modeling the XZ plane, but the analysis will be 3D. So we can move on the XZ plane, so you see the structure. Okay, so what do we have here? Let me collapse all the nodes so I can show them one by one. Okay, so starting from the geometry. We have here a bridge made of 3 segments, and here I have 3 polylines, okay, three edges. The deck left, which is this one, okay, deck right, and then deck center. They are completely detached because later on I will show you how to include the contact here between the separated decks. Then we have other 2 points completely detached from the structure, which are here. So support left and then support right, which is over there, here. They are detached because, as I said, we are using isolator systems here. So I cannot apply the boundary condition directly on the deck, but instead I need a duplicated node here. Here I will have the boundary condition, and then here we have a zero length element for the isolation device. Okay, that's why we have these 2 extra vertices. And then we have some groups here of piers. Okay, so all the piers are basically polylines. One is this one, and then the others, and then I group them together. This is not mandatory, but sometimes it is useful to keep this word tree clean. Okay, so I selected all the piers and I used the make compound. This one is just used to create a group. Okay. These ones are made of 3 segments. So the main pier here, and then we have the headings, and you can see them. If you switch on the property, you can see the extrusions. Okay, so this one is the main pier, and then you have 2 different headings there. Okay, so let's go back to the geometry. What do we have then? Then we have other 2 groups. Okay, isolators bottom and isolators top. Why? So if I switch off the interactions, let me just select all the geometries. So select, 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 and let me select the deck, and I show them only. So I switch off basically the interaction. You can see that we have these polylines up here for the decks. Then we have these polylines here for the piers and headings. And then we have a bunch of separated points. Why? Well, first of all, because we have a certain offset from the deck to the headings. So we wanted to consider this offset. That's why we decided to move the deck upward. And then we will use a kinematic constraint to create a rigid link between the deck and the top node of the isolators. Okay. Then we have the nodes at the top and the nodes at the bottom, just because we need to put isolators there. Okay. So basically, we are going to have a rigid link on these three nodes here, then rigid links up here to create the offset between beams and the top of the isolators. And then here in the middle, we will have zero lengths for the isolation system, okay? And this happens basically everywhere. Okay, now in this first model, I will not include contacts. So here, I'm not going to create any interaction. We will do it later on in the second example. Okay, now let me switch everything on. So this is all about the geometries. Then we created some selection sets. Selection sets are basically groups, okay? So basically we decided to model the piers as nonlinear elements and the deck, which was not expected to go into a nonlinear state, as linear elements, okay? And then I decided to create two selection sets, and you will see why, but basically we will use them to assign different Rayleigh damping, okay? So we have a set for nonlinear elements, which are basically all the piers, okay? Without the headings are modeled as linear, so just the piers. And then we have a linear set for all the other stuff. Select. Okay, so all the other geometries, but not the interaction, because the interaction are either kinematic constraints or isolation systems, and I don't need to assign damping to them, okay? So here we have everything. So this is all about selection sets, geometry, and now the interactions. As you know, in STKO, we use interactions to model those things that cannot be modeled as a geometry. For example, springs, zero-length elements, kinematic constraints. So basically, the interaction, as the name suggests, is a component that make two separated geometries interact with each other in some way, through boundary conditions or through other elements. So how many interactions do we have? Well, we have a bunch of interactions for the isolators, and I will explain why we have all of them. But then we have the rigid link horizontal. If I select this one, you will see that they are all at the bottom. Basically, we will use all of them. I decided to create all these interaction in a single interaction because basically all of them will have the same boundary condition, okay? So there is no need to create them separately. Once again, this has been done to keep the worksheet clean, okay? So in every interaction here, the node of the pier is the master, and the nodes of the bottom nodes of the isolation system is the slave, okay? And they will be connected with a rigid link kinematic constraint. This is just to create an offset between the isolators on the left and on the right. Then we have another rigid link, which is called vertical. Select, and once again, all of them. And they are used to create the offset between the deck and the pier. Okay. Also here, I use the bottom node as master and the top node as slave. But here it is not important. I mean, you can switch the slave and the master. This is not important. Instead, here in the middle, it is important that the master node is the central one. And then we have all the isolators that are modeled separately. So starting from the leftmost side, here we have the isolator left. Then we have the isolator right, which is on the other side, which is this one. And then all the isolators numbered from the number of the piers. So isolator one left, one right, two left, right, and so on. Why did I decide to keep them separated? Well, basically because when you start designing the isolation system, it may happen that you cannot use, the exact same isolator everywhere. You may need to change the properties to make sure that that isolator is working well in that place. So if I create this interaction in one single interaction, then I can assign only one material property. Since I knew from the beginning that I had to change eventually the isolator properties, I decided to keep them separated, okay? That's why we have all of them. So selection set geometry interaction. Here we are done with the geometry of the model, okay? Once you have done all this stuff, the geometry is fine, okay? And then you have to proceed with the next components, which are those that define the OpenSees model. Okay, so the CAD is the built-in, is the group of built-in components that we have in STKO that of course will be translated into OpenSees elements. But to make this translation, we need to proceed from definition down to the analysis steps to create the OpenSees components. So in definition, we always create the time series. Okay, so since we are going to create first a vertical analysis for gravity and then a dynamic analysis for the earthquake, we need basically 3 time series. The first one is a linear one. Okay, so just a linear time series. We go in time series and which is linear, and it is fine that is go from 0 to 1 and from 0 to 1. Just because it is a static analysis, so the time is not important, and we are going to apply the vertical loads incrementally. And then we have 2 path time series for our accelerograms in X and Y. Now these accelerograms last about 40 seconds. Now for reasons of speed, I will analyze only the first 15 seconds. Then of course, if you want to analyze everything, just go to the analysis and change the total time to 40. And the time step is 0.005 seconds. Oh, by the way, I forgot to tell you, but for those of you who are new to STKO, STKO is just like OpenSees, is unitless in the sense that you don't have to define a unit system in the software, but you have to know what unit system you are using because you have to be consistent with the values that you input. In this case, I'm using kilonewtons and meters, okay? So just to let you know what unit system I'm using. So once we are done with the definition, we can go with the physical properties. Now here we are going to use fiber elements for the piers. Let me go to the properties so you can see the extrusions. So fiber elements for the piers, then the headings and these small slabs here are elastic. The girder and slab here for the main deck is still elastic here now that the ultimate strain is a little bit too much. Let's say 0.4 or even more. So let's go past the ultimate strain. So here, for those of you who are new to STKO, whenever you define a new material, which is already in OpenSees, here you have all the properties. The names are the same that you have in OpenSees. Here you have a link to the OpenSees manual. But here you have a tester. So you can test your model either in a monotonic strain protocol, or you can use any of the others. So you can see how it looks like in a dynamic, cyclic settings. Let's see, for example, how it works in a cyclic environment. Okay, so it's very useful to use the material tester to understand how the material model is working. Okay, so this one is for the unconfined concrete. Then we have the same one, but for confined. Okay, the ultimate strain is a little bit more. Let's test it. Okay, so this one is the confined concrete. Then we have an elastic concrete. As I said, why do I need an elastic uniaxial? At least 2 pairs of stress strain points, okay, in each direction. If you want, you can include the third one. And it can be unsymmetric in tension and compression. And the next thing is that here you can play with the pinching parameters to make this one like a standard elastoplastic material, or like a more peak-oriented material, or more like a pinching one. Now let's see in this case how it works. Symmetric linear increasing, this is fine, just times steps. Let's see how it works. So this one is the shape of my constitutive model. If you play with these two here, you can change the behavior. For example, if I put 0.5 in both cases, let's see what do I have, okay? More like without any bumping here. If instead we use the first one, is what I did before, so let me invert it, 0.5 and 0.25, you should have a pinching effect instead of the previous one. So let's go back in 0.25 and 0.5 that was working for me here. The next thing that I have here is the fact that you can include the cyclic damage, for example, due to energy. This is nice because, for example, when you're doing a dynamic analysis, and you want to simulate the strength loss due to the to cyclic damage. Here you can, for example, with a value of 0.01, if you increase the number of cycles, let's see what happened, 30 cycles. As you can see now, it starts losing, degrading the strength. If I increase them even more, you can see it goes almost to 0 here. So this one is a nice material to simulate all these effects. And it is the only one that you can use to simulate cyclic damage when you use a fiber cross-section, because actually no concrete model is able to model this kind of cyclic degradation, because basically it comes from the rebars, okay? And if you use materials like the steel 01 or steel 02, they don't have it. From what I remember, the only other material that includes cyclic degradation for steel is the reinforcing steel material. The problem is that it has some convergence problems. So when I want to include cyclic degradation for steel, I always choose the hysteretic. Okay. So here we are done with the uniaxial material. Then of course we need to define the cross section. So the first cross section is for the pier. Okay, so pier section. I decided to use a rectangular fiber cross section because the pier has exactly a rectangular shape. So as you know, in STKO, you can create fiber cross-section either with the fiber command or with the rectangular fiber section. Now, the fiber command is to create generally shaped cross-sections, and this is the one that I used for the deck. I will show you later on. Or if your fiber cross-section is rectangular, you can use this automation here, which basically allows you to define a rectangular cross-section with few parameters. And it has also another value here that it allows you to compute the confined concrete if you don't want to compute it manually. Now, this was not the case because I decided to compute manually the confined concrete. Okay, so basically here I defined GJ, which now is mandatory in OpenSees, and then all the dimensions for my cross section, all the rebars. There are many of them because, of course, this is a very large pier. And then I have a concrete for the cover and another concrete for the core. Okay. Now in STKO you have this option that if you do not include the core material, and if you put none here, then this tool will compute the confined concrete for you based on the amount of stirrups here and based on the code that you choose. Now in my case, I compute it manually, so I will put it directly here. So confined concrete for core. That's fine. So this one is the fiber cross section for the pier. Now, since this one is quite thick, I also wanted to include shear deformability, because as you know, when you use a force beam element, if you do not include any shear law in the section aggregator, the force beam column will behave as an Euler-Bernoulli beam. Now that is fine for slender members, but in this case it is quite thick, so we need to include shear at least elastically. Okay. Now in this case I was not interested into the nonlinear behavior shear. I just wanted to define shear deformability. So I created a uniaxial material that has the shear modulus of concrete times the shear area. Because since I'm going to use this one into a section aggregator, I need to provide not just the shear modulus here, but the shear modulus times the shear area. Now in this case it is a rectangular cross section, so it's 5/6 the gross area. And then of course you can create a section aggregator where you use a cross section for the PMM interaction, and then the same uniaxial material for shear in both directions. Nothing for torsion, because torsion is already included into the fiber cross section. Okay, once we have the fiber cross section, we create the beam section property, where basically we decide the integration scheme, in this case a Lobato scheme. Then here we choose the pier aggregator and the number of integration points. Now I choose only 3 because it is sufficient. I don't have any linearly varying load. I have just distributed loads. So 3 integration points is perfect. And I don't need more of them. And this one has been assigned to, if you want to check the assignment of this one, to all the piers. Okay, fine. So going on, the header. Now the header, as I said, they are elastic. So I just needed to create an elastic cross section. And here you have a tool to create an elastic cross section of any shape. We have here a database of many shape types. And in this case, it is a simple box cross section. And then you provide E and G, okay? So this is fine for the header property. Then the other property will be, once again, Lobato integration rule with 3 integration points. Now, when you have to create an elastic element in OpenSees, you have 2 options. You either use an elastic element, or you can use a force-based element with some integration point with an elastic section. I always prefer to use this option here, because then I can go into the Gauss points and see what's going on inside the element. Of course, the elastic one, the completely elastic element, is faster, but I mean, you don't need to be, you don't need to optimize your model, because this one is pretty small. Okay. So the other property, if you want to see where it is assigned, you can click select, and you can see all the headers here have this property. Now going on, I need to define the deck section. So the deck section has a custom shape, so I cannot use an elastic section here because I don't have this shape. So you can either use an elastic section, and you can go here and choose custom instead of one of these predefined types. You define custom, but then if you choose custom, the representation will be a circle, okay? So in this case, I wanted to show a nice representation, so I decided to create a fiber cross section with elastic elements. So this one has a general shape, so I cannot use the rectangular cross section, but I need to go with the standard section, fiber section here. So basically here you decide the dimension, we are in 3D. Here you can open the fiber cross section editor, okay? And basically here you have some CAD command to draw your shape, and then you can mesh it. Now the mesh is not extremely fine because it is elastic. I mean, I don't need a very fine mesh. And all the things here, they have a mesh of pretty much 10, and the material is the elastic concrete, as you can see. Okay, I can cancel it. And once again, I need to create the property for this one. And also this thing here is just a Lobato scheme, 3 integration point, but with the deck section, okay? And if I select this one, I will see all my decks that are selected. Fine, so we have just one extra cross section for the slab here near the joints. That basically this section here is made of girders and slab. Here we have only the slab, okay? So once again, an elastic section with a rectangular cross section, so I don't need to waste time here. If I select this one, okay, you see the target selection. Fine, so basically up to here we finished assigning physical properties to all the frame elements, and now we need to define the physical properties for the isolators, okay? Now for the isolators, since we are going to use a zero length element, we need to define uniaxial materials in the different directions. Now in this model I needed 4 different kind of isolators. So I defined 4 steel 01. I decided to choose the most simple approach for the isolator, so using a bilinear material. If you want, you can use bearing elements, okay? But this is another topic. We are going to cover this topic on the next webinar when we will talk about friction pendulums. So here we have just a bunch of bilinear materials, okay? Simple steel 01. If you look at the values, they are larger than standard values just because we have, since it is a frame element, if I switch off the visualization here, we have just one interaction here, but of course we have many isolators along the beam width. And this value here is the sum of all of them. I don't remember if there were 2 or 4, I don't remember, okay? So this value is the sum of all those values. Well, so as I said, I have 4 of them. They are slightly different. And then I also have 4 different uniaxial material for the stiffness in the vertical direction. Okay, so this one, the vertical behavior is just linear, and each one has its own stiffness. And then we have a small rotational stiffness about the y-axis. and it is equal for all of them, okay? And it is this small value here. So once you have uniaxial material for all the degrees of freedom that you need, and in my case, I only need X and Y to be nonlinear, Z to be linear, and rotation about Y. Now, I don't need anything about the rotation about the Z and X axis because I will apply a constraint there. So once you have all uniaxial material for your zero length, you can go here, you can create a zero length element, okay? And then you say, okay, I want a zero length element. It should be 3D and 6 degrees of freedom, so displacement and rotation, because it is going to connect beam elements. But I want to use only 3 degrees of freedom. The first one, which is the X, the third one, which is the Z, and the fifth one, which is rotation about Y. So in the X-axis, I use the T1, so the nonlinear material. Then in Z, I use the KUZ of the appropriate type. And then here I use the rotational stiffness, which is equal for all the 4 types of isolators, okay? And this is the same for all the others. Now, if you want to see where I assign these properties, let me go in front view. These are the isolators. You can either click here and click on select. So you can see, for example, the T1 has been assigned on the first one here and the other selected. Otherwise, I decided, for example, to change. This is another thing that probably I've never explained in our webinars, but you can change the shader. So the way it looks like in here. So that basically you can show different colors. For example, the first one was a blue line here. Then the other tabs, they have a different color palette here. Okay, so green here, these two are different, and so on. So you can easily identify the different types of isolators. Okay, so now with the isolators, we finished creating all the physical properties. And as you know, physical properties in STKO means all the OpenSees components that define the constitutive behavior. So material sections and eventually zero length spring elements and all this stuff. So once you're done with physical properties, you need to define the element properties. Element properties instead are used to define the kinematic behavior and the finite element formulation that you want to use for a certain geometry. Keep in mind that if you forget to assign an element property to a geometry, that geometry will not be converted into an OpenSees element because, of course, STKO doesn't know how to convert it into an OpenSees element. So all the frame elements are converted into force beam columns. So if I select this one, you will see all the frame elements. Okay, so they will become force beam column. And here in the force beam column, I decided to use the rotational transformation type. Now for the transformation type, you just need to choose which kind of transformation it will be. It is linear, so small kinematics, P delta, or co-rotational. Instead, the axis for the orientation will be given automatically by STKO using either the default ones, okay? Or if you want, you can assign your own local axis, okay? So STKO will take the local axis, will take the type here for the transformation, and will create a geometric transformation object, okay? So let me switch off the local axis visualization. And then we need one other finite element, which is the zero length. And this one is assigned to all the zero lengths that we use for the isolators, okay? And let's see how it looks like. It's just a zero length, so you go under element model, zero length, standard zero length, so not all this strange here. You just need to specify that it is in 3D, okay? And this one is assigned to all the interaction from isolators. Once you have done this, you also have all the element properties defined. The next step are the boundary conditions, okay? So if I go on condition here, you can see the boundary conditions. Now the first one is a fixity in all 6 degrees of freedom. So all the bases of the pier are selected, as you can see here, and also the base node of the abutment here, okay? Here and on the other side. That's why I created this extra node, because I couldn't fix this one because I needed an isolator in between. Then we have a bunch of beam uniform elements for the self-weight, okay? So we have self-weight pier, which is a sign on the piers, okay, along the piers here. And then we have self-weight for the header, which instead is a nodal load placed on top of the beam. Then we have self-weight for girder and precast flank, which is assigned on the beams. Now, as you can see, we have many loads applied on the beams. I decided to keep them separated by types, okay? But actually, they could go together and sum all of them. But I decided to keep this model clean to separate the different load types. So we have the self-weight for girder and precast flank, the self-weight for the deck slab, always located on the same beams. Then you have always on the same beam on top there, you have also the self-weight for the diaphragm, parapet, handrail, and pedestrian concrete. Then the asphalt and the lane loads. Okay. And then you have the self-weight as nodal forces for the bearing elements, and of course are located at the points of the bearing elements. And these are all the forces that we have, okay, for the vertical analysis. Then we have some boundary conditions, some kinematic constraint, and we have the rigid link. And if I click on edit, a complete rigid beam, so 3D of type beam, which means I couple all the degrees of freedom, translational and rotational. And as I said at the beginning, it is assigned to the bottom constraint to couple the base of the two isolators to the top of the beam, okay, as a rigid body here. And then it is also assigned to the two vertical interactions to simulate the rigid offset of the deck with respect to the beam, okay. So rigid links. Then we have equal DOF in Y for the isolators in the Y direction, so in the out of plane direction here, because there are some supports that avoid movement in this direction. Okay, so that's why in the zero length element, I did not assign any material in Y and rotation about X, so torsional rotation here and rotation about Z, just because I have an equal DOF there, so I don't need to put any extra material in there. So these one are the only two kinematic constraint, multi-point constraint, and this one is the only single point constraint. And then we have a lot of masses. Now we have translational masses here and then rotational masses. I will spend a few words on rotational masses, but let's start with them. So for all of them, they are mainly edge masses corresponding to the beam uniform load or nodal masses for the nodal forces, no? Okay. So, for example, the mass of the pier is basically, here, this is a nice feature that we have in STKO. By default, it is constant, okay? And it is a vector where you apply your values. Otherwise, you can apply them as a function. Now, typically, this is used, for example, if you want to write a value that is function of the spatial dimension. For example, if you want to create a linear varying load along the height. But sometimes it is just useful to explain to the user what you're doing here. So for example, I took the same value that I had for the vertical load, and then that value is divided by the gravity acceleration, divided by the other dimension of the beam. So you can understand what I try to do here when converting a load to a mass. Okay, so as I said, it is not mandatory, but it is useful to let other people know what you are doing. So the same has been done for all the other things, okay? So for example, the asphalt is another mass that we place on top here, and so on. So every load that was defined here has been converted to mass down here. And then we have rotational masses. Now, most of the time, we do not include rotational masses because they are not influencing so much the analysis, especially if you discretize the model. And now I'm going to show you why we decided to include these masses. Now, first of all, I want to show you that if I go on the mesh, you can see that I discretize the model. So instead of using just one element for every geometry, I decided to split them in three parts, okay? I decided to have more elements just because I'm doing a dynamic analysis, and as you know, you can obtain the exact solution for a force beam element with just one element for each member. But this is true. This is not true, for example, when you want to do eigenvalue analysis, because you cannot obtain the exact eigenvalues with just one element. Or for example, when I'm using the co-rotational transformation, if you discretize your model, large displacement and rotation will be captured better. Now, another reason for doing a discretization is because then the translational masses that are here, for example, are located at a certain distance from this point. So they will generate some sort of rotational masses about this point here. But this happens only for rotational masses about the y-axis. Okay, so the translational mass in z here will create a rotational effect around the y-axis, and rotational mass in y will create a rotational effect around the z. Okay, but as you can see, there is nothing that can create rotational effect around the x-axis of the beam. So if you go on the rotational masses here, so let's say for example the rotational mass for the girder, which is this one. As you can see here, we computed the same mass, the same translational mass, then divided by the length and then multiplied by the moment of inertia, the second moment of area on this direction, and only about the local x-axis of the beam. Why? Well, basically because, let me try to do a model. Let me try to do an annotation here. If you remember here, we have a cross-section that is quite thick, something like this, okay? Now, if I model this one, and of course it extends all over. If I model this one as shells, okay, then I would have many nodes along the width of the slab. And then each one of them would have the translational masses, for example, in Z. And the translational masses in Z, given by their distance, will create some sort of rotational effect around the x-axis. But this is a beam, so all the translational masses is lumped at the center. So I don't have this kind of masses here that create this rotational effect around the x-axis. That's why we decided to include rotational masses down here. So clean. Okay. And so, of course, as you can see, all of them are only defined about the local x-axis. Perfect. So now we finished with the boundary condition, and then we have all the analysis steps. Okay, now I will explain the analysis step, and I will run the analysis. So the first one, this one is not mandatory, but it is just a custom command to start the timing, because I wanted to know how long it takes. So whenever you cannot do something in STKO, you can always create a custom tickle script and put whatever you want. So this gives you the maximum flexibility. So here I will put a custom script to save the initial time using the clock command. Then I will do a bunch of stuff here, and at the end I have the time end. Okay, so once again I call the clock command, and then I print. Okay, this is the elapsed of time. So time end minus time start. Now, in between these two custom steps, I have the first one, which is the recorder. As you know, we use the MPCO recorder. The MPCO recorder needs the file name, and in this case, it could be implicit bridge. Then nodal results. For nodal results, I just want displacement and rotation, reaction forces and reaction moments. Here, I also checked modes of vibration, because before doing this analysis, I was doing an eigenvalue analysis, but here it is not necessary anymore. Then results on elements. I want local forces, which are basically the element forces at the end nodes. But then I also want the element forces and deformation along the frame, so section forces and section deformation. Then material strain and stress. I need them because material strain and material stress are basically the forces and deformation of continuum elements, but they are also forces and deformation for zero-length elements. And so I need them because I want to monitor what's going on inside my isolator system, which are modeled with zero-length elements. And then finally, I want to visualize also the stresses and strain inside every fiber. So I also checked section fiber stress and section fiber strain. Remember that if you want some custom element result that is not among this predefined list, you can always go here and do your own. So imagine you have your own finite element that has your own material, which is not available in OpenSees, and you have, I don't know, something which is called plastic deformation, and it is defined as a uniaxial material, and you want to plot it, you can just go here and click and type section dot fiber dot the name of your result, for example, plastic deformation. Okay, and this one will allow you to record also this custom result. Then what else you have? The record frequency. So how many times you want to record? By default is always. So every time we have a convergent step, it will record something. Otherwise, you can have a DT, so a time increment. For example, I want to record every 0.1 seconds or every number of steps. Okay. And finally, you have the region option. If you want to record only a sub-portion of your model, for example, if you want to save disk space, you can say, okay, I want to monitor only what's going on one peer, so I will record only one peer. Now, in this case, I go with the default, so I want to record everything in terms of time and everything in terms of geometry, okay? So this is my recorder. Then, second step is to apply boundary conditions constraint, okay? So single point and multi-point constraint. As I told you before, in single point constraints, we only define the fixities. So we include it here at the beginning, and then we define two multi-point constraints. Okay, so the rigid link to create the offset between the two isolators for each peer, and the offset between the isolators and the top deck. And then we have another multi-point constraint, which is the equal DOF in the y direction, in the out-of-plane direction, to avoid the relative displacement of the isolator along the y direction. So this is all about single point and multi-point constraint. Then we need to apply a load pattern for vertical loads. Okay, so here I have a vertical load pattern. As you probably know, you go here, you go in pattern, add pattern, load pattern. And for load pattern, you have to choose the time series. And for vertical loads, we choose the linear time series. And then you need to put the loads here. Of course, you have simple loads, so nodal loads, which basically have this self-weight here. Then you have the element loads, so loads distributed on elements. And you have all the line loads that we defined previously. And eventually, you may have single point constraints like imposed displacement, but here we don't have any of them. Okay, and then we are ready to run the static analysis. So for the static analysis, we just choose the penalty method for constraint, because if you remember one of our previous webinars, I told you that when we have a lot of kinematic constraints, such as equal DOF overlapping with rigid links, it is difficult to use the transformation method. Why? Because, for example, here, if you take these nodes, for example, and let me do a simple annotation. For this constraint here, this one is the master node, and this one is the slave. But then I have another constraint here, where this one is the master, and this one is the slave. And then I have another constraint here for the equal DOF, okay, where this one is the master, and this is the slave. And the transformation method cannot handle it, because, for example, this master here, which is this node, cannot be a slave on another constraint, okay? So when you have this kind of complex situations, instead of using the transformation or plane constraint, you should use the only one that is available, which is the penalty method, okay? So that's why you will see them using penalty method here and also in the dynamic analysis. For penalty method, pay attention to the penalty values that you choose. In previous webinars, I've already been talking about this one. So you can compute the expected maximum stiffness of your model, and then you add 8, and you will obtain 15 in this case. Okay, so that one is the optimal value for penalty method. Then we have a sparse solver here, Krylov-Newton method, a check on displacement. The test should be done on displacement when you use penalty. Never use a check on the unbalance, otherwise you will never converge. And then we do a load control with 10 time steps, a total duration of 1. Okay, so this one is a static analysis. When we have done with this, we reset the time step to 0, we keep the load constant, and we call a wipe analysis. Okay, once we have done this, this static analysis, we can simply add the two uniform excitation, one in X using the time series acceleration X, and the other one in Y direction. Okay, so you choose the direction Y and the acceleration in Y. Then you define the damping. Now, how you can define damping in STKO? Well, of course, you have to call either the Rayleigh command in OpenSees or the region command in OpenSees. Now, if you want to apply damping onto your entire model, you can just go to the this command Rayleigh. Okay, this one we've called the Rayleigh command, and in STKO you have an automation here to input the frequencies and the damping percentages here, and then you will obtain the damping parameters. Otherwise, you can go with the manual imputation of the two damping parameters. Okay, but now in this case, I don't want to apply damping everywhere because my peers are modeled completely into a nonlinear fashion. So I include all the nonlinearity in the peers, both from a constitutive point of view through material nonlinearity, and from a kinematic point of view using the rotational approach. So I don't need to specify any further damping for the peers. So in this case, I cannot use the Rayleigh command. I need to use the region command. Okay, so I create a region using the selection set for the linear group of elements. That's why at the beginning I've shown how to create selection sets, because at the end of the day I wanted to apply damping only to the linear elements. Okay, and then I choose these two values that come from a model analysis using an equivalent effective stiffness for the isolators. Okay, and now to do this one is a kind of iterative process to find the secant equivalent stiffness for the isolators. Now this is not the topic of this webinar, so just take these values for good. And then of course with this region I want to apply the Rayleigh command. So up to here you define damping for all the linear elements, but not for the peer and not for the isolators. Then we can create another analysis command, but this time it will be a transient analysis. Okay. Now all the other settings are the same: penalty method, reverse CMK. Then we have the same sparse solver, Krylov-Newton also here. Test on displacement for the same reason as before. We are using the penalty, so we need to check the displacement increment. And then we need to go to the integrator. Now, this is where I've been talking about, let me go back to the PowerPoint, implicit dynamics. The analysis in OpenSees is always the same. So it is the same analysis command with a transient analysis. It becomes implicit or explicit based on the time integration scheme that you choose. Now, in this case, I'm choosing Newmark with 0.5 for gamma and 0.25 for beta. And this one defines the average acceleration method, which is an implicit method. Okay. Otherwise, you have other integrators. For example, the central difference for the explicit or some other explicit down here, or you have other implicit methods. But let's say the most commonly used one are the Newmark for implicit and the central difference for explicit. Okay, so Newmark, average acceleration, time step. Now in this case, I want a total analysis which is about 40 seconds, but as I said, to avoid wasting time here, I will analyze only 15 seconds. And I want 3000 time steps because the time increment in my records up here is 0.005. Then I choose an adaptive time step because in STKO we have the default, which is fixed time step, which is the same thing that OpenSees does by default. So you define the time increment and the number of increment, and then OpenSees tries to analyze all those increments. If it finds a convergence problem, it stops. Instead, if you choose adaptive, STKO will generate a script that tries to reduce the time step if it finds convergence problem, or it can increase the time steps if the convergence is very good. Okay, and here you have a few parameters to control how the adaptive time step reduces or increases the time step. okay? So for example, here I don't want the time step to increase over 0.005, but if it finds problem, it can go down up to 1 to the minus 6, the initial time step, and so on, okay? Now the load const here is not necessary because I don't have any other analysis after this one. Also the wipe analysis is not necessary, but in any case, this one is the end of the analysis, okay? And finally, you have the time end to get the timings and print what's going on the screen, okay? So let me run this analysis, and this one will take about 2 minutes and a half, okay? So let's save this one. Before you run the analysis, make sure you mesh your model. Okay, now in this case it was already meshed. But when you go to the mesh, the first thing that you have to do is to define a seed. Okay, now in my case it was a uniform by size with 5 meters, if I remember properly. And then you build your mesh. Okay, eventually you may want to create mesh controls, but this is not the case because I don't have surface or volume elements. Okay, so linear elements are just linear elements. You don't need to specify any complex mesh control. So once you have done the edge seed that define the mesh size and the mesh controls that define the algorithm, for example, structured or unstructured, or the interpolation order for the element, it can be linear, quadratic, and so on, you're ready to create your mesh, and you can build your mesh, okay? Once you build your mesh, you obtain these things here. So the discretization of your model. Finally, there is the partition command, which is used if you want to run parallel analysis of a huge model. And in that case, you can decide to partition your model, for example, in 1, 2, or 3 partitions, okay? Now, in this case, I don't want to do this because this model is pretty small, so let's make sure you don't have any partition. Perfect. Now, when you have done this, you can just choose one of the solvers that you have. For those of you who are new to this webinar, if you remember, STKO is just a pre and post processor for OpenSees. It does not include OpenSees. You have to have your own OpenSees installed on your computer, and you can link STKO to as many OpenSees versions as you want. Now, in my case, I have 2 predefined OpenSees version installed on C, OpenSees solvers, and so on. I have an OpenSees and a parallel one for OpenSees NP. And then I have 2 other manual, which is the OpenSees that I'm compiling for myself, okay? So for example, if you want to make some modification to the default OpenSees, you can keep on adding your own kits. And this is fine for people doing, contributing to OpenSees code, okay? So if you want to test your own version, you can do it here. When you have defined how to link the STKO to OpenSees, you can just select the solver that you want. Now in my case, I want to use the default one, the sequential one. When you have done this, you can run the analysis, okay? At the beginning, it asks you to where you want to save the TCOL files. By default, it is the same folder where you have the input file, okay? Okay, now we can wait, first analysis, and then the dynamic analysis. Here you have the percentage of the analysis. It will take about 2 minutes, so let's wait a second. And then after this, I will show you how to post-process this file, how to understand what's going on inside your model. And finally, I will show you that with this model, so without the contact element between the bridge decks, you will see some, even small, but some compenetrations of the central deck with the other 2 decks here. And then I will show you how to add the contact. Now, if you see here, there is a perfect convergence. We just have 2 iterations, 2 at most 3 iterations for every time step to reach a norm of 1 to the minus 7 or 8 meters. So it's perfectly fine. You will see instead that when we add contact, and contact is a very bad nonlinearity, you will see that in some places it will start having problems. So the adaptive time step will try to reduce the time step, and then when it passes the strong nonlinearity, it will go back to the initial time step. Okay, but as you can see here, the nonlinearity is pretty small, so there is no problem in convergence at all. Okay, so we are 80%. Now, of course, when you want to run this analysis, when you download it tomorrow and you want to run the entire analysis, just change the timing here from 15 to 40, which is the total duration of the accelerations. Okay. Okay, here we're done. 100%, and it is about 2 minutes. Okay. So as I said before. And of course, this is the output of this custom command here. Okay, so perfectly. Once you have done your analysis, you will find this one, the SCD is the input file for the STKO. And the MPCO is the file produced by OpenSees. And then you have all these STKO files, which are the files produced by STKO when you either write only the input file or when you run the analysis itself. Then you have another file here called MPCO data, which is just a small support file for the MPCO recorder. That, well, basically the problem here was that when we implemented the MPCO recorder inside OpenSees, OpenSees does not give any information about the shape of the cross-section. So we just put the shape of the cross-section in this file. This is not mandatory. You can also remove it. But if you have it, you have a better representation in the post-processing, okay? So just to tell you what is that file. So when you have finished with the pre-processing, you go in post-processor and you click on Open Database. Now I need to go inside the folder of my webinar. In this case, it is AUX implicit bridge, and you open up the MPCO file. Okay, here we are. I can switch off the grid here. Now by default, well, this is our MPCO recorder. Here we have the results on nodes, all the results that we asked for. Then we have the results on elements. Now, if you remember, we had local forces, and then we have, for example, section deformation. So you may say, why do I have 2 of them instead of 1? Is this a duplicate? No, this happens basically when you have 2 different elements that gives different components for the same result name. So for example, the top of the bridge, the deck, has been modeled as an Euler-Bernoulli beam. So force beam column with just a fiber cross section. So it does not have the output for the transverse shear. That's why I have only 4 components. I have epsilon, curvature about the z-axis, curvature about the y-axis, and the torsion. Okay. So these one are the 4 components given by the fiber cross section, 3 coupled, and the torsion is given by the GJ parameter. While for the pier, I use the section aggregator. So the result given by the pier element is different. It has 2 more components, which are the shear deformation or shear forces in case of forces. Okay, that's why you may have some duplicates. Same thing for where is it? Material. Local force, for example. This local force here comes from the 0 length, so you have only 3 forces, while this local force here comes from the beam element that have 6 components. Okay, that's why in this new version we decided to put the components here in the name so that you can easily identify which result you want to visualize. Okay. So the first thing that you can do to understand what's going on in your model is to create a plot group. Now by default, STKO, whenever you open a PCO file, it creates a new plot group. Otherwise, you can create it with this command here, and it creates a surface color map, which corresponds to this command here. So this is the default. When you select the color map, you can change some of the parameters. For example, here I want to increase the deformation scale to 10. Okay, then if you want, you can change some of the parameters here. For example, I can switch off the feature edges, so I can see only the, or if you don't want to see the section extrusion, you can switch them off, but I prefer to take them into account. And then if you want to play an animation of this, you go on the plot group, and then you can play with the timer slider here. You can either move it as you want, or you can run it manually. You can specify the delay. You can save the file to the video to a file. So now it is not important. Now, if you play an animation, you will see here, for example, that we are going to have some kind of pounding here. here and then on the other side also. Now to make sure, later on I will make sure that this bounding is happening, because of course don't be fooled by the fact that I used a deformation scale. When you increase the deformation scale, it may happen that it looks like it is compenetrating, but actually it is not. So I will show you later on how to identify if two elements are compenetrating. Okay, so once you check the deformation, you make sure that, well, typically the first thing that I do to make sure that my model is fine is that there is no strange deformation, because sometimes it may happen that you forget to apply a boundary condition or you forget to assign an element. So the first thing that you can do is to visualize if everything seems okay, at least from a visual point of view. Then you can start extracting data here and there to visualize in detail what's going on. So for example, if you want to visualize, if you want to export, I don't know, the quantities on a pier. Now let's say in this example, you were designing the seismic isolation and you want to make sure that the piers remain in pretty much an elastic state. How can you do that? So I remove the surface color map and I create a gauss-point plot. Why? I want to visualize the values on the entire cross section. There are along the element member. Now there are two ways to do this: either the Gauss-point plot or the beam diagram plot. You can create it directly from here or from the toolbar. So the Gauss-point plot will just give you an output. Now let me choose the result, for example, section deformation on the piers, and let's say the curvature, and let me increase the Gauss point a little bit. Okay, so you can see a bunch of particles, so this kind of balls here, that are located exactly at the location of the Gauss point, and their color and size are modulated by the result. Okay, so in this case you can see the exact result and exact position. The other option instead is to use the beam diagram plot. Okay, now in this case this is the normal stress on this decks here. It is not important. I want to visualize instead, for example, the curvatures on the piers, curvature in Y, for example. Let me decrease the scale a little bit. Okay. So also with this one, you can see what's going on along the member of your elements. But this one is only visual. So if you want to extract a result, you need the Gauss-point plot. I will show you why. So Gauss-point plot. You choose the result that you want, and in my case it is section deformation with 6 components, because 6 components, as I told you before, is on the pier. Okay. Then I don't care about this result. I know that the maximum deformation can be on the bottom. So let's say I want to check this pier here. So I select the Gauss point on the bottom, and I go on chart data, extract chart data. I want to extract result on Gauss points, so I click on element Gauss point, next. Then I have 2 stages. Stage 1 is the vertical analysis, stage 2 is the time history analysis. So I want to extract results only for the 2nd stage. And I want to plot, by default you have a result on the Y data, on the Y axis. And in the X data, you have the pseudo time step by default. But in this case, I want to plot a moment curvature. So I want to use another result here. So in the X axis, I want section deformation with 6 components. And I want curvature about the Y axis, which is the curvature about the axis. Let me do a notation. The local axis on my beam are, let me do it again. I need to annotate. Yeah. This one is the x-axis. This one is the y. Okay, and then I have the z-axis on the other direction. Okay, so I first want to see the bending about the y and then the bending about the z. Okay, so with this one selected, I go back to extract chart data, Gauss points, stage 2, user result, section deformation 6 components, curvature about the y-axis, and then section forces 6 components, moment about the y-axis. Next, the Gauss point has been already selected, which comes from the first database, which is the only one that we have, comes from the element 54, which is this one, and comes from the first Gauss point, which is 0. This one would be 1, this one would be 2. Okay. So next, and I want to call this one moment curvature about the y-axis, and I also want to create a chart. When you're done, you click on finish, and basically it creates a data here, which is linked to the database. So every time you change the database, this one will be updated. And you can copy paste it if you want to post-process it in Excel. And here you have the chart representing this one. Now, when you may ask, why do I see this strange behavior? Well, this is quite typical when you are using fiber cross-section in dynamic analysis, and I will explain you why. Now, before doing this, let's extract the same data about the y-axis, about the z-axis, sorry. So once again, I keep the previous selection, I extract data on Gauss points, as before on stage 2, but this time I want section deformation and curvature about the z-axis, and here I want section forces, 6 components, moment about the z-axis. Next, and this one would be MKZ. Okay, so this one seems a little bit nicer, but the point is that if you ask why I'm obtaining this kind of things, well, it is just because the fiber cross section has a coupled behavior. So as you can see, it is actually being activated on both X and Y, but also on the axial stress. Because typically we assume that axial stress remains pretty much constant during the analysis, but this is not the case. For example, here I may want to extract the variation of the normal stress along the time, and you can do it like this. So stage 2, use the pseudo time step, or actually you can do something, yeah, let me do it first like this. So use the pseudo time step, and I want to monitor the section force on the pier, but the normal stress, okay? So the actual forces. Next, and I call this one n versus time. As you can see, it is not constant. It starts from 3,000 kilonewtons, and then it starts oscillating of about 5,000 kilonewtons, up and down, okay? So that's why when you see the moment curvature, you can see this kind of jumps. Just because when it is loading in bending, it is actually moving about the surface. If you remember the, let me do an annotation here. If you remember the interaction diagram is something like this. So you have My, Mz, and then you have the axial stress. And then the beam diagram is something like this that goes around this axis. Now, of course, when you start moving about the y-axis, for example, the moment curvature can be something like this, but then you change the amount of stress, for example, the amount of normal stress that goes from here up to here, and the strength decreases in bending. So you may see a sudden jump. Then you see, for example, the stress comes back here, and then it gains once again the bending moment. Okay, that's why you see this kind of staggered, this kind of confused curve. Okay, so don't worry about that. For example, if you want to make sure that this does not happen, for example, in something that is uncoupled, you can extract the same data, but this time in the zero length. So, for example, you want to see what's going on inside your isolators. So I can go on the lateral side, and let's say I want to see what's going on the isolator. Now remember that isolators are zero length elements, so they're basically springs, and what happens in the different direction is uncoupled. So you will not see this kind of effect in the isolator. So for the isolator, I need to visualize their Gauss points for selecting them. So I need to visualize the material strain, for example, and here I have the Gauss point on the zero length. Let's say I want to monitor what's going on this isolator here. So extract chart data, Gauss point, because this is a Gauss point, the only Gauss point inside a zero length. Next, stage 2, use a result. And then I use material strain with 3 components. In the first direction is the actual direction, so where I put my nonlinear behavior. And then, likewise, I do material stress in the first direction. Next, and this one is actually force versus displacement of the isolator. Okay, now as you can see, the isolator is perfect. You don't have that kind of staggered behavior as you have in the fiber cross section, just because the isolator is not being influenced by what's going on in the vertical direction, because they are basically 3 uncoupled springs. Okay, so this is perfectly normal. Now, the last thing that I wanted to show you is how to, well, of course, in this case, in the practical case, you see that the piers are going into a quite nonlinear state, so probably we want to change the properties of the isolator system. Okay, but now this is not the topic of this webinar. We are not talking about the design of isolators. The last thing that I want to show you, for example, in this kind of analysis, you may want to see if the assumption of not using any contact here, let's see if it is fine or not. So here we have a gap of 15 centimeters, okay? I want to find out if I have a kind of compenetration here. Let's see how can I do it. Let me go here and let me switch on the nodes so that I can select them. Then I go on chart data. This time I want to extract displacements, so I go on chart data on nodes. Next, stage 2. And I want to plot displacement versus time in the x direction. First on the left side, and I call it u left. And then I do the same on the right side. And you can call it, once again, second stage, ux, and this one will be u right. Okay, once you have these two here, you can go and grab them, and you can do some post-processing, for example, I don't know, in Excel. Actually, in the new version of STKO, we will have the Python interpreter also in the post-processor, so that you can directly perform this kind of operation from inside STKO. But now let's do it here. So this one is the displacement on the left, and this one is the displacement on the right. And let's see the difference between them. So this one would be right minus left. Okay, let's see the minimum of them, because I want to see compenetration. So the minimum is 0.25, so 25 centimeters, accounting for, initially I have an initial gap of 15 centimeters, okay? So I have a compenetration of 10 centimeters. So probably the assumption of not using a contact was not enough. Okay, so you know that there is a whole topic about the pounding. Sometimes it can have it can give problems on the decks, it can induce damage, or the unseating of the decks. So let's say in your case you are worried about this compenetration and you want to make sure that this is not causing any problem to your analysis, okay? Because every time you do a nonlinear analysis, it is a compromise between the complexity of the model, okay, and the speed of the analysis. So sometimes you don't want to include certain nonlinearities because they can mess up your model. Contact is one of them, and you assume that you don't need them. But of course, the fact that you assume that you don't need them, it doesn't mean that you don't really need them. So you have to check that your assumption was right. Now in this case, I have some kind of compenetration, and I want to make sure that this is not giving any problem. So I go back on the preprocessor, and basically now we'll do my change here, but in your case you will find the modified version. So this one implicit bridge will be the one that I've just run now, and the other one with the contact is here, okay? Now let me go pretty fast here. How did I define the contact? Well, the first thing that I've done is to create an interaction, okay? So a new interaction, and I call it contact, let's say CT. Okay, and then I need to select the master geometries. So the first master geometry will be the left node on the first deck, so the right node on the first deck, and the other master geometry will be the right node on the central deck. Right click, so the nodes on the left basically. And the slave, so select the slave geometry, will be this one and the other one here. Okay, and right click. Now basically STKO creates an interaction connecting each slave to the nearest master. So you have one interaction here and one interaction over here. Okay. Now that I have them, which is this interaction here, I need to create the contact element. Now in this case it is a simple unilateral contact with an initial gap. So I don't need to create a real contact element, I just need a zero length element with a gap material. So how do you find the gap material? You go under physical properties, and I call it contact. You can go under material uniaxial, some standard, and then you have elastic, perfectly plastic gap. Now, I don't want to use the plasticity here, so the first thing that you have to simulate is no compenetration. Now, for no compenetration, you need an infinite stiffness. Now, of course, this is not possible, and you need to provide a sufficiently high stiffness. Now, do not exaggerate with this value, because if you put the stiffness value here, which is much larger than the other stiffness values, your stiffness matrix may become nearly singular, okay, or ill-posed. So typically what I do is, for example, let's say this contact element is to avoid pounding between the decks, okay? So I take the actual stiffness of the decks and I use that one increased by a couple, 2 or 3 order of magnitudes, okay? So 1 to the power of 10 here is more than fine, because I have something to the power of 7 for the actual stiffness of the concrete. Then the area is about 20, so the order of 1. So the total actual stiffness is something on the order of 8 or 9. So 10 or even 11 is fine. Now I don't want to provide any plasticity, so I just want pure contact. So here I can put any large value that I want. Now in my case it should be an elastic, a perfectly plastic gap in compression and no strength in tension. So I put a negative value here, 1 to the power of 100. Here, yes, I can use any large number because this one does not enter the stiffness calculation. It's just a limit, okay? So here I can put whatever number that I want, okay? Don't put 1 to the power of 1000 because it does not exist in, of course, in the floating point numbers, okay? And then I need a gap. Also, the gap should be negative to let it understand that I want contact only in compression. And my gap was 15 centimeters, okay? Now you can test it. For example, let's push it down to 0.2 in compression. And then I also do some test in tension, in cyclic. So let's see how it behaves. Now this is perfectly fine. So it goes from 0 to 0.15, which is the my gap. And then after the gap, it soon goes into a very stiff response, okay? So this is fine for contact with gap. And as you can see, tension is not doing anything. Let me do more cycles. Okay, so it is not going anywhere. So let's try it in tension. It is 0, so perfect. This is exactly what I want. No strength in tension and contact in compression after a gap. So this is fine, but this is a uniaxial material. Here I need a zero length element, so I need to create the zero length property. So let's say this one will be contact spring. I go here, special purpose, zero length material, 3D, U, and displacement and rotation, because it is connecting two beam elements, so they have 6 degrees of freedom each one. But I only need the axial degree of freedom, okay? So the first one, and I choose the contact material. Okay, so in this case, I created the material for a zero length, which only has 1 degree of freedom. And I assign it to this one, and also the other one. So you can select your interaction and simply drag and drop the property. Now I have to do the same for the element property. So I select them once again, and I can assign the same element I used for the isolator, because by the way, yeah, I called it isolator, but actually it is a zero length. So the same element that I used for the isolator here is also fine for the contact element. So I simply drag and drop zero length onto this new interaction. Okay, so I don't need to do anything more. I just need to remesh it because I changed my geometry. So as you can see, I don't have any mesh here. And if I try to run the analysis now, you will see that I have an error. It says geometry 131, deck left has not been meshed. Please build the mesh command. Okay, so you go here and you build your mesh once again. So now I have my mesh and I can run the analysis. Now you will see that at a certain point I will have a convergence problem, but fortunately the adaptive time step will allow me to pass those non-convergence points. And in fact, you will see that I will have 3 or 4 of them, I don't remember, but exactly in the points where there is contact. Because as you know, the contact is a very complex nonlinear behavior. So let me run this analysis. Also here we take about 2 minutes. So up to here is running fine. You will see as soon as it starts struggling with convergence. Let's see. Here is fine. Now I should have a small nonlinearity almost. Let me see. See here? Let me stop it so you can see what's going on. Up to here it was fine. That an average of 2 or 3 iterations, but then up to here I am decreasing the time step due to a non-convergency. So it went from 0.05 to 0.04. Then it managed to solve this one, and then it starts converging again, but this time with less iteration. So I am increasing once again the time step. Then I am decreasing it. So it is trying to find the optimum time step to solve this nonlinearity. As soon as it finishes, it starts going back with the initial time step. So as you can see here, the time step is pretty small compared to the previous one, which is 0.05. Now it's almost 1/2 of that. And now it will start gaining back to its initial time step. Okay, now it passed that nonlinear stage. And as you can see now, it's back to the initial time increment. Now I think it will happen, yeah, also there, and another couple of times. But I think I have 3 points in which those decks go in contact, and we will see them in the post-processing. Or probably, yeah, probably not, because when I did this test, it was happening on the, yes, here, and probably some others at the end of my accelerogram, but here I cut the analysis at 15 seconds. So probably if you try to run the entire analysis, you will see other points in which the 2 decks go in contact. So remember that here I'm only analyzing half of the entire acceleration. Okay, so we're almost done. 100%. Now it took a little bit more, almost 3 minutes, because of course we had those nonlinear problems, those convergence problems. Now I go back here, and I can literally reload this file, because now in my case, I did not create another folder like here. I just modified this file. So when I run OpenSees again, it override this MPCO file. Okay, so as you can see, it has been overwritten here. So I can just reload it. Okay, now it will reload everything. It will recompute all those charts, and then we can go and see what's going on. Okay, so let me see this one. It's the implicit bridge. That's fine. let me go back to the surface color map, and let's see if something happens here on the displacements, if we can see something. Okay, here actually from the displacement you are not able to see, but it can be see some kind of banding here. Now, if you want to see what's going on, let's go back here. I remove the deformation scale to 0, so I don't see any deformation. And let me find where is the... Now, as you can see now here, we have the contact element. And let's see if I can find something. So, this is the displacement on the left side and on the right side. It should have been updated. So let's change it. Let's go here and I place it here. And then let me go back here. And I pass them here. Yeah, so probably I didn't change something. Let me see. Because in the file that you can find there, you have the contact. Let me see if I go on the surface, gauss-point plot. Material strain here, and I want to see material stress. Material stress 1, okay. And I want to see somewhere if I have larger than 1 stress. So Gauss points, stage 2, material stress, this should be the contact force. As you can see, yes, I have it here. Yeah, so probably I have to re-extract these files because now the meshes are changed, so I need to extract them once again. Okay, but as you can see from this last here, at a certain point on the left-hand side of this deck, I have 0 contact stress, but at a certain point I have a high contact stress. This one means that at this point of the analysis, about 7.5 seconds, I had compenetration in the previous analysis, but now I don't have compenetration because I have this contact force. Let's see what happens on the other side, because if I remember properly, I had 2 more points of contact. Let's see. Stage 2, material stress. Yeah, here I have 2 points of contact, the same as before, and on the other side there is another contact, okay? So let's try to extract again, for example, this one. Let's try to extract again the nodal results. So this one is the left one. Extract on nodes, UX, stage 2. And this is the displacement on the left. And I do the same on the right. Next, you right. Okay, now let's go here, you left, copy and paste it. Now, okay, now it's changed. Yeah, probably there was a mesh renumbering. Then copy this one and paste it here. And as you can see, the compenetration is almost 0. It's not 0 because I assigned a finite stiffness. Okay, so to have 0, you need to increase that contact stiffness. But of course, you don't want to increase it so much. So as you can see, there is no compenetration now. And if I want to make sure I can copy paste this one. Let me go back to the top. I can copy paste this one, which is the difference between the 2 displacements. And I can literally unlink this one, paste it here. And if I plot this graph, I can see that here there was a first point of contact. As you can see, it is trying to go down 0.1, but it can't. Okay, so here there was contact. Due to some convergence error, you can see that it is not exactly 0.15. Sometimes it goes back, or probably to dynamic effect, so it pounds and then jumps back. And then the same happens on this second point of contact down here. So this one is the way you can make sure that there is no compenetration. Now in this example, the compenetration was not that much. So in only 2 points, only 10 centimeters, but not many times, okay? So probably yes, the assumption of not using the contact was fine, but in any case, this is how you check it. Now, this one allows me to introduce to the last part of the webinar, which is explicit dynamics. Now, what you've seen here is that this kind of analysis can be easily done with implicit time schemes. Of course, you may have convergence problems, but if you have properly set all the convergence tests, and if you use an adaptive time step, you can easily try to go through the convergence issues. The problem is that when you add strong nonlinearities like contact, okay, you have seen that it soon makes the convergence much more difficult to overcome, okay? And in this case, it was a simple unilateral contact. Remember that instead, in real life, friction contact is much more difficult to solve because you don't have only normal contact or unilateral contact, but that one is coupled to frictional contact through a more Coulomb-like criterion. And most of the times you don't have that contact only in few located places. Sometimes you have contact all over two huge contact surfaces, and that is very difficult to solve for the Newton-Raphson method because it is a very strong nonlinearity. So in those cases where you have to solve for highly nonlinear problems, for example, including contact or including fracture and this kind of stuff, you can do the explicit dynamics, okay? So let me close this one, and I will show you very briefly some examples, or actually one example. And this one will be, let's say, the first example in our webinars for explicit dynamics. We will come back on this topic with other webinars because it is a very complex topic. So yes, I want to close this one. Oh, I need to attach this one. Give me a second. But it's fine. We have 10 minutes. Okay, so let's go back to the presentation. So I first go to the explicit dynamics. Okay, so what we have seen up to now is implicit. Now, what is the explicit dynamics? Now, the equations are always the same, of course, but we change the integration scheme from implicit to explicit. Now, in explicit dynamics, you can see that everything depends only on quantities on the previous time step. So we can easily solve for the acceleration, okay, just by a simple inversion of the mass matrix. And then we obtain the displacement at the new time step. We don't need to iterate. That is fine. So we don't have problem of convergence. The problem is that this method is not conditionally stable. We have some conditional stability. Okay, and this one basically means that the time step is limited or bounded by the highest frequency of the system. Now, computing the highest frequency of an entire system is a massive task. Now, in this case, it is feasible because the model is small. But if you have a large model, computing all the eigenvalues is not feasible at all because you need to do a full matrix inversion and eigenvalue problem on full matrices. So the alternative way is to limit the time step doing an element-wise operation. For example, computing the minimum time step based on the characteristic length of every element and based on the elastic wave speed of every element. Now, the characteristic length depends on the size of the elements, on the integration scheme. Now, I'm not going into details. And the elastic speed wave it can be computed like this for 1D elements, so Young modulus over the mass density, square root of this one, or this one for 2D elements, or this one for 3D elements, okay? Now you can see you can look at many references for this, but keep in mind that the time step should be limited, and you should use an element-wise criterion, because using the full frequency of the model is not feasible. Now, just one side note. This one, if you try to do some calculation here using common Young modulus and Poisson ratios that we use in structural mechanics, you will see that the time step in explicit dynamics will be of the order of microseconds. Okay. So just give me a second. I need to attach the microphone. Just a second. Otherwise, it will go down in battery. Can you hear me well? Okay. So if you try to put here in those equations the typical Young modulus and Poisson ratio and mass density of common materials, you will see that for structural mechanics, the time steps is of the order of microseconds. So this means that it takes a lot of time steps. A lot of time steps because, for example, if you want to analyze 30 seconds of ground motion, I'm a bit far, but unfortunately, it should charge. Okay, we'll try to speak louder. So imagine if I want to analyze those 30 seconds of ground motion, it will take 30 million time steps if I am on the microseconds, and it will take a lot of time. So typically, explicit dynamics is used for fast dynamics. For example, when you want to analyze blast or fracture or impact, so something that lasts less than 1 second. Okay, so that will be feasible. Now we show you how to, a simple example I've done on a masonry wall using a micro model, very small model because otherwise it takes a lot of time. A smaller one and then a larger one, which is made in parallel. And here we take this one, this example to show you how to do element removal based on a custom criteria. Here I have a video for the output where I will show you directly from STKO because for some reason here I cannot see the video. So let's go here in STKO. Okay, so I just want to show you what is the input file so that you can have a look at it if you want to run this model. Keep in mind that running this analysis here will take, for this small model here, which is not very large, will take something like 6 or 8 hours with only one process. But it is fine because here you can start playing with explicit dynamics and see what's going on if you change the time step or if you change the mass properties and so on. So very briefly, here this is a masonry wall. You can see that this explicit model with bricks and mortar joints. This is just a small specimen, 1 meter times 1 meter, so not that large. Here I have my nonlinear model for mortar and a layer shell for the mortar. This one has been modeled as shells because I want to model an out-of-plane, the effect of the blast coming from the explosion of a blast here. So it is like a 50 megapascals of pressure applied with a fast reflective blast. The pressure of the reflective blast on the surface. Okay, the law is a kind of exponential tendency. This is the material for the masonry. I'm pretty sure the mortar, the brick. I'm pretty sure the brick will remain in elastic regime, so I'm using an elastic membrane plate section just to save time. Then I have a shell element, which is the new one that we implemented in the new version of OpenSees. And I'm using the rotational transformation because I want to use large displacement and rotations for this kind of examples, because we will see extremely large rotation in this example. Then we have distributed phase mass. Okay. Now here the typical this model is made in Newton and millimeters. So the mass density for masonry or concrete-like material should be 2.5 to the minus 9. Here is to the minus 7 because the thickness of the wall is 100 millimeters. Okay, so this mass should be multiplied by the thickness. As I said before, in this case,
we typically don't need rotational masses because the model is well discretized. It's a shell model, so there is no need to apply rotational masses. The only problem is that when you do that explicit dynamics, then we go back to the equation, you don't have the stiffness matrix. And like in this example, I don't even use the damping matrix because I'm including all the nonlinearity directly in the model. So the only matrix that I have is the mass matrix, which is diagonal due to the lump mass approach that I'm using. But I need to invert it. Now, inverting the diagonal matrix is pretty fast because it's just an element-wise inversion. The problem is that every element on the diagonal of the mass matrix should not be zero. Otherwise, this inversion is not possible. That's why when you have rotational degrees of freedom, you cannot keep that as zero. Okay? So just put a value which is pretty similar to the translational one. They have some boundary condition. You can see it when you download this file, but it basically speaks on the borders here. It speaks on Z only on the bottom because here we have a vertical load. Then we have this vertical load up here. Then we have distributed body forces all over the wall. Okay, and then we have the blast force. The blast force has been used with an equation. I told you before that you can assign a force as a function, not only as a fixed value. And this function is function of x and z. To apply this kind of increasing power in the middle. If you want to see what this function looks like, you can plug it into, for example, MATLAB. And if you do a mesh grid, you can plot this kind of pressure. Okay, so this one is the distribution I'm using on my shell. So slightly uncentered here in the middle. Okay. So let me go back to the STKO. This is fine, and then the analysis steps. So the first thing that I do is to apply boundary conditions, single point constraint. Here I don't have any multi-point constraint. Then I add the vertical loads with the linear time series, which is this one. So pretty similar as before. Okay. Here we have only two vertical loads, body forces and added load. Then we do a vertical analysis. Now in this case, yes, I can use the transformation method because I only have a single point constraint. Use a sparse solver here, little Rapson. This one is a standard static implicit analysis, so I need to do some iteration here. And then I have blast load, which is simply another load pattern with blast time history. I slightly increased it to because it was defined as a maximum of 5 megapascal here in the time history, and I multiplied it by 3 to reach 15 megapascals. And then here I have the blast pressure load. Okay, then I have a recorder here because I didn't want to record the vertical analysis, so I placed the recorder right after the vertical analysis. Then I have some monitors. Monitors are used to monitor the what's going on in the analysis in runtime. You will see what it looks like when you run this file. But basically, I'm monitoring the displacement of a node in the y direction, its displacement on the z, because I imagine that when it explodes, it goes in y and then slightly fall down here. And then I was also monitoring the reaction forces. Okay, then I define a selection set for the mortar. So select, because I want to perform element deletion. Okay, so I want to delete element based on the damage that they accumulate. And the only elements that I want to check for are the element in the mortar. Okay, that's why I created this selection set. And now the analysis is not a standard analysis as they do in OpenSees, like this one. So I didn't go here and press analysis because I wanted to do something special inside the analysis. So whenever you want to do something that is not available in STKO, you can just create a tickle script and do your own stuff here, okay? And I'm running out of time, so I will try to be as fast as possible. So this one is the analysis that I set. So transformation, plane number, system diagonal, because as I told you, in this kind of explicit analysis, the mass matrix is diagonal, so I can take advantage of this system, which is much faster. Now, the test command is not necessary. I need to input it just because it is required by OpenSees, but it will never be used. So here you can put whatever you want. The algorithm should be linear whenever you do an explicit analysis. And then you have to choose an explicit integration scheme. Now the default is the central difference, but I found that it doesn't work with element dilation because of the way it's implemented, so I use the HHT explicit. You can use it the trapezoidal one or the one without trapezoidal, it's the same. It is important that here this value is bounded between 0.67 to 1. 1 means non-numerical damping, 0.67 is the maximum numerical damping. Keep in mind that if you use numerical damping, you have to further decrease the time step, and I don't want to do that, so I don't want any numerical damping here. Then I define the transient analysis. Here I do some stuff for the critical time step, and then I start doing my analysis. Well, I save some values to monitor how many elements I removed. Then I do a loop here for all the increments in my number of increments. I just run one analysis at a time. Okay, so analyze one. When I'm done, if everything is okay, I do some stuff that STKO does by default, and then I do my own script for doing the element removal. So what I do here, then those of you who are more coders can look at the code. But basically, I go inside all the elements, I find which one of them, I get the result from an element, getting the response, which is in this case the section information, and I check the maximum membrane principal value. Then I do the same for bending deformation, so the maximum principal curvature, and then I found the maximum shear deformation, and then I take the maximum of them. If the maximum of them exceeds a certain threshold, I say that this element should be removed. And then I perform the removal of an element. If an element is removed, then I need to change the domain and reset the system to diagonal because it has to reshape the system matrices. Okay? And this one will be repeated every time. Now, if you try to run this analysis, you will see how it works, you will understand, you can try to play with the time step size to see what's the difference between the results. And here I already have the result done, so let me show you the result of this one. Be prepared because running this analysis, even if the database is small, it is going to take, I think, 4 hours, and it is a small model. Okay, so let's see what's going on here. So basically, I apply a plus pressure here. Let me change the color a little bit. Okay, deformation of 1. Whenever you have large displacement, do not increase the deformation. And here in the first stage, you see that due to the pressure, here you have a displacement in the middle, exactly the shape of my custom node. And then soon some elements start exceeding those large deformations. Okay. And they are removed. They were removed by my code. Okay, as you can see, using your custom code, you can define your own way. Now, basically, here you can see how it works. Now, all these elements are detached to the explosion, and due to the bending here, also the mortar layers here are completely gone. So these elements here will now drop to the ground. Okay. And here you can see the effect of very large deformation. So explicit dynamics can be used to perform this kind of very, very complicated analysis, but be prepared that it will take a lot of time. Okay? And be prepared that it is not simple. You need to iterate a lot of times to calculate your own time step. You need to perform element dilation. Sometimes even only element dilation is not so simple to do. So explicit dynamics is very complex. We will come back on this topic in future webinars, but this is just to show you that OpenSees is able to do it. And with STKO, you can create your own custom scripts to also do this kind of analysis. Okay. So we are done, and thank you for participating to this webinar. It was a little bit out of time, but we still have some time for questions. So if anyone has questions, please. I stop sharing my screen. Please, if you have questions. Question 1. Is there contact interface element between mortar and bricks? No, there is no contact between mortar and bricks because basically when I do this kind of simulation, the material model that I assign in the mortar layer also contains the nonlinear effect of the interface between. So it's basically a lumped constitutive model taking into account the elasticity of the mortar and the fracture of the interface. There are ways for doing this kind of approach. Otherwise, you can model the interface between the brick and the mortar and then modeling the mortar, but that kind of analysis will take much longer and I don't think it is necessary. Could you provide some information regarding possible explicit solvers? Yes, actually we are actually evaluating all the possible explicit solvers that are in OpenSees because not all of them are documented. So we are in a process of testing all of them. The first thing that I can say, let me share my screen so you can see the questions of other people. Oh, we are here. The first thing that I can say now is that central difference is the typical one that I would use, is the standard one. The problem that I found with the central difference was mainly from an implementation point of view, because whenever you remove an element, you have to update the domain. But when you update the domain, the central difference goes back to its initial state. So basically, at the first element that you remove, your explicit analysis cannot go on. So that's why right now I'm using the HHT explicit. So for the moment, Alexander, you can use that. In the future, we are in the process of evaluating all the explicit time integration scheme that OpenSees has to offer, and we will provide a documentation for that. Do we need not to apply damping to nonlinear elements? This is another topic. Damping in general is an alternative way of including a nonlinearity that you are not including in your model. The point is that it depends. I mean, if you model something that's linear, of course you have to use that. If you model the nonlinearity, it depends, because sometimes you model the complete nonlinearity, like large deformation, contact, friction, plasticity, cracking. Sometimes you only model some of them. So it's up to you. I mean, you have to find out what value of damping you need to apply on nonlinear elements, depending on how much nonlinearity you have physically modeled. Of course, it would be an error if I apply my 5% of damping also to my nonlinear elements here, because here there are all sorts of dissipation already modeled in the model. Okay? Which formula was used to measure reflective pressure for blast? Actually, I took them from an experimental test, but there are formulas. This one that I used, it is actually similar to an exponential. Let me see this one. It's not completely correct because what I found for I think that there are some formula for reflective waves, but they are slightly different. The formula would be something like this: so it goes up, down, and then there is a negative pressure, and then it goes to 0. Okay. Now this one has been simplified just by using an exponential that goes to 1, and it has been taken by a paper. I will share the reference in the content files. The only thing that I've done is to smooth this thing here, this kink, because basically one of the problems in explicit dynamics is to try to avoid shocks. So using a load history that's without kinks, so that it's pretty smooth, will allow for better convergence. So this is one of the reasons why I use this kind of series. Additionally, it would be interesting to show how to handle parallel sequential explicit analysis. Of course, why I decided not to talk about the parallel one here, because in sequential analysis, as you've seen, I use the diagonal solver. Okay. Now there is also the diagonal solver for parallel analysis, which is called NPI diagonal. The problem is that it has a bug. I was trying to use it. These days, but I've seen that there was a crash. Now I have to go inside the OpenSees code and try to find where that crash is. That's why I want to move the discussion on parallel explicit on future webinars. Next question: could you recommend a procedure to determine frequencies for Rayleigh damping coefficients? Actually, it is stated by some of the national codes, but you have to take the first one and the last one that provides you a certain amount of participating masses. I think it was the 85%. Now it depends on the situation. Sometimes you don't reach them, sometimes you don't want to include all those higher frequencies. But let's say you have to compute the range of the frequencies you need to do a certain excitation of masses. UA, will it be possible to use explicit analysis for model involving highly nonlinear material? Yes, of course. This example is one of them. So highly nonlinear in the sense when you have softening mainly. Of course, you can use explicit. Actually, you can use explicit also for linear analysis. The problem is that it doesn't make sense for linear analysis. But for every time you have extreme convergence problem that cannot be solved by the implicit solver, you can use the explicit one. Now, I do not recommend to start with explicit right away because it is a very difficult topic. Your analysis should be really fast. In the sense that it should be a fast dynamics. You cannot think about doing, for example, a structure interaction under an earthquake. So you have one model with millions of elements for different seconds of analysis. It is something that will take days and days. So you have to start playing with explicit solution and try to understand how it works. How equilibrium achieved after brick gets isolated from masonry? Will the model have become unstable? No, that's why, this is why I use dynamics and explicit dynamics. Let me explain you why. In static problems, yes, when a brick completely breaks, so for example, let me go back to post-processing. Like in this case, a brick is completely detached from its support. Okay, so for example, this brick here is not sustained by anything. In static problems, of course, it is singular, okay? Because you only have the stiffness matrix. That matrix is unconstrained, so the stiffness matrix has 0 eigenvalues, and the problem is unstable. In dynamics, you don't only have the stiffness, you also have the mass here, and so you also have mass on these elements. So in dynamics, you can simulate something that actually falls down, okay? So when an element is not attached, in dynamic analysis, it doesn't mean that it is unstable. It's simply dropping, okay? It is unstable if you do not assign a mass to it. That will be unstable, okay? So for example, let's say I forget to assign mass on this element. This mass here will have a singular stiffness and 0 mass, so yes, it will be unstable, okay? In TLC script, we need to ensure mass metric inversion not to be a trouble, right? Not in TCO script. I mean, mass matrix inversion for mass is guaranteed if you apply a mass to every degree of freedom, okay? To every free degree of freedom. In that case, the mass will be diagonal because every element in OpenSees, only the solid elements, but every element in OpenSees apply a lumped mass approach. And if you apply masses at the nodes, it will be diagonal. The only problem is that you have to make sure that every degree of freedom has a mass. So for example, if you do this model here and you remove the mass from the rotational degrees of freedom, it will be singular. Okay? So you don't have to ensure, you just make sure that the user assigns masses everywhere. And if it is not like that, it will OpenSees will issue an error. It will say the diagonal at the index 10 is equal to 0, so I cannot invert. There is no need for you to check. Okay? OpenSees will start by itself. Is material required aesthetic material? Yes. It's an aesthetic material, and I prefer it when doing dynamic analysis. I prefer the aesthetic material because it shows, first of all, because you can modulate how large the envelope should be, the aesthetic look should be through the pinching parameters. And second, because it can include segment degradation. So when you have dynamic analysis, where we are forces to remove the constraint and substitute which force on reaction, expression you get, absolutely. So when you have dynamic analysis, where you are forced to remove the constraint and substitute with force from reactions, the reaction. So the essence should the acceleration at the top some No, actually, I did not understand this question. Why are you saying that?
Yeah, can I ask in person, which is potentially is better? When we do the soil structure interaction problem, and we do the dynamic analysis, we remove the constraints and we substitute with the reaction, right? So at some, so we have no, we have not anymore the application of the acceleration, but of some forces. So my question is, since we are getting some acceleration both at the bottom of the model and at the top, the acceleration that we are getting are absolute and not anymore relative, because there is no fixed.
Exactly. No, I understand what you're saying now. In that case, the acceleration are absolute because not because you remove the constraint, but actually because you did not apply an acceleration using a uniform excitation. You applied a stress, and that stress is causing an acceleration. Okay, so in that case, it is absolute. The only point in OpenSees where the acceleration are relative is when you apply the acceleration at the fixed degrees of freedom using a uniform excitation. Okay, that is the only one.
Thank you.
Okay, can we do an IDA using TCI adjustment command? Yes, actually, using TCO, provided that you know enough TCO, you can do whatever you want. This is the nice thing about OpenSees, is that since it is programmable, you can do whatever you want. Okay, something is easy, something is more complicated, but you can definitely do it. So I'm just curious, is it possible that the current model from explicit to implicit co-simulation? You can try to perform the implicit. For implicit, you mean yes, you can in the same simulation, you can. For example, in this case, I did implicit for the vertical load, explicit for the second. In this case, for example, you can even say, okay, let's say that I want to use implicit dynamics until my model converges. If I have problem, I switch to explicit. Yes, you can. The TCO script that I've written here should be modified in such a way that it starts doing the implementation with an implicit solver. And the first time it finds a huge nonlinear problem, it switched to dynamics. I didn't think of it, but yes, it can be definitely done. This is the nice thing about OpenSees, is that it is not only implicit or explicit. There are many softwares out there that are only explicit. Okay. In this case, it has both implicit and explicit integrators, so you can do a co-simulation. Oh, thank you for taking part in this webinar. Can we use varying elastomeric in bridge models instead of isolators from info? Of course you can. We gave a previous webinar using elastomeric bearings. So that's why in this webinar the focus was not on modeling the isolator devices. So yes, you can use the elastomeric bearings element. And in the next webinar, and I have it here, in the next webinar we're going to use the friction pendulum. There was a previous webinar here, the 12th webinar, seismic isolation, where we're using the elastomeric bearings. Is there a limit for the pressure pulse? Not, but I mean the higher the load you apply, or the smaller is the time step, yes, it increases a lot the acceleration. So it may happen that you need to reduce the time step because it is seen as a very shock problem. Okay, so every time you increase the shock, for example, to with a load applied in a smaller time step, yes, you may need to reduce the time step. Keep in mind that the equation that I gave for computing the time increment, they are just a first guess of the time step. Typically, you should use a time step which is much smaller than this one, because as you can see, this one depends on mass and elasticity. Now, mass remains the same because of mass conservation of mass. But the fact that you see the elasticity here, you soon understand that it is not going to remain constant because the young volumes soon can degrade. That's one of the reasons why I use element dilation. That's one of the techniques to avoid reducing the step too much. Other problem is that when you are using large deformation can induce very large distortion of the element, and also in that case the characteristic length increases. So keep in mind that you can do a first evaluation of the time step using this formula, but then the time step depends on many other things. If you include damping, the time step decreases. If you include shock loads which are higher in intensity, the time step decreases, and so on. So yes, explicit dynamic is a mess. I mean, you need a lot of experience to start mastering it. When we do explicit analysis, do we always set system as diagonal? No, I mean, you are not forced to use diagonal, because a diagonal matrix is a subset of a general matrix. It is simply faster, because if you know that your model is diagonal, and for being diagonal, you need to have only the mass matrix. If you include the damping, if it is only proportional to mass, it will be diagonal. If it is proportional also to stiffness, it will not be diagonal. Now, the other problem is that the diagonal solver is only available for sequential OpenSees. There is a diagonal solver for OpenSees and P that I said is not working, and in the next days I will try to find the solution for that. Was earthquake applied at the bottom support constraint of peers? Yes, because I used the uniform excitation. Whenever you use the uniform excitation, it will be applied to every fixed node, okay? Or every node that are fixed in that degree of freedom. If instead you want to selectively apply a ground motion, okay, only at certain locations, then you have to use the ground motion command, not the uniform excitation. Was it quick attend? Okay. In STKO, I have manual, especially for advanced model selection. Only CPU is there. From where I can get the info to learn how to make these models. What do you mean? Let me see. When you are here. It's only models, but then you can go through the examples here. And they are explained step by step. Well, actually, yes. No, here for the advanced model, we need to complete the documentation. But actually, these models, some of these models or similar, are treated on our webinars. Yes, in this case, we need to complete this documentation. You are right. The documentation is something that is always a work in progress. But we were going to improve the documentation in every new release. And also, I remind you that you can go on the our webinars and you can download all the files here. Okay, so everything we have done in previous webinars are available through the video recording on YouTube and the content files. Okay. Okay, and thank you everyone for participating in this webinar. Well, if there are no other questions, I would like to thank you, all of you, and let's see you on the next webinar. The next webinar will be on, let's see, Thursday, February 18, and it will be on seismic isolation using frictional pendulums. Okay. So once again, thank you everyone for taking part in this webinar, and look forward to see you in the next webinar. Thank you everyone.